This is 40 Days of Chemistry, Part 3, and by popular demand, we're looking at 9.3.3, acids, pH, strength, and concentration. Jumping right in, what is an acid? Very important if we're looking at acids, and there's two ways of looking at acids. The first one we learnt was the Arrhenius model, which is an acid ionizes in water to produce hydrogenizes the only cation. Now that's still commonly used because it's simple and easy to understand. Most acids are in aqueous solutions, so it's relevant. And it also allows us to calculate things like strength of acids based on percent ionization and the fact that pH is related to the Arrhenius model. And according to the Arrhenius model, acids ionize in water to produce hydrogen ions, and these sort of equations here are things you see for the Arrhenius model. For strong acids, note they're going to completion, whereas weak acids, they are in equilibrium with their ions. But the better model and the better way to explain acids, the one I want you to use in your HSC, is that acids are proton donors. And the reason we use that is because this Bronsted-Lowry theory, or this Bronsted-Lowry model, explains everything the Arrhenius model explains, but it does more. It explains non-aqueous solutions, non-neutral salts, buffers, and more and more and more, but that's coming up in 9.3.4. The one difference, though, is when we're talking about the Bronsted-Lowry model, we replace H3O plus for H plus in our pH calculations, and that's because, as we know, acids being proton donors, they actually react with water. They donate protons to the water to produce the hydronium ion, whether that's in completion for strong acids or whether that's in equilibrium for weak acids. They all produce that hydronium ion when they donate their proton to water. Now we understand what an acid is, let's move on. The first thing we need to understand for this part of the course is some example common natural acids and bases. Starting off with bases, some common natural bases are things like ammonia, which is found in urine, calcium carbonate, which is found in limestone, and metal oxides, such as the metal ores, iron oxide, magnesium oxide, calcium oxide, etc., etc. We know metal oxides are bases. Based on our work in 9.3.2, we learnt that the left-hand side of the periodic table, the metals, form basic oxides. By that note, looking at natural acids, obviously the non-metal oxides are our acidic oxides. So don't forget things like carbon dioxide, sulfur dioxide, and nitrogen dioxide are our acidic acids. Some other example natural acids: hydrochloric acid found in your stomach, and there's the formula for hydrochloric acid. Sulfuric acid, it is found in acid rain and volcanic springs, but most of the time sulfuric acid is an industrially produced chemical. It's the number one or most commonly produced industrial chemical in the world. H2SO4, it's diprotic, it's got two protons it can donate, and these are the two protons it can donate in a reaction. The next one is acetic acid, is its common name, or ethanoic acid is its systematic name. It's produced by the oxidation of ethanol, and that's natural because fruit naturally ferments, and that fermented fruit, which is ethanol, will be turning into acetic acid quite naturally. And here is our formula for acetic acid. It has got 4 protons, but only one of them can be donated. It is monoprotic, and this is the one there that can be donated. And this obviously is the carboxylic acid group, this COOH group, and therefore this is the hydrogen in the acid group that is donated. The next one we need to know is citric acid. Citric acid is its common name. We have to know its systematic name as well. It's 2-hydroxypropane, 1,2,3-tricarboxylic acid. You have to know that name, and you have to know the structure. Here are the 3 carbons making up the propane background. Here is the OH group, the hydroxy group there. One thing to note, it is the oxygen bonded to the carbon, so please always draw the H, the O, and then the C. The next thing is the tricarboxylic acid, and here are our 3 tricarboxylic acid groups. Now note, it has got 8 hydrogens in total, but only 3 of them can be donated. It's the 3 in the carboxylic acid group. So these 3 hydrogens here are the ones that can be donated in acid-base sort of reactions. Lastly, a little common misconception is that citric acid is not the same thing as vitamin C. Vitamin C and citric acid are both found in citrus fruits, but vitamin C is a different acid. It's called ascorbic acid, so please don't make that mistake. Citric acid is not vitamin C. Let's move on. The next thing we've got to look at is some uses of bases in acid. First of all, bases are used in cleaning products. For example, ammonia is used as a floor cleaner. It's also used in agriculture, such as things like agricultural lime, which is added to acidic soil to raise the pH. But acids are used in a range of things. We looked at industrial processes, e.g. sulfuric acid. We know it's the catalyst in esterification and dehydration of ethanol, and there are many other uses of acid in industry. But the ones we've got to focus on for the course are acids in foods. And there is 5 main ways that acids are used in food. First of all, for flavour. For example, vinegar and citric acid are added to food for flavour. These two relate to preservation, but citric acid uses an antioxidant. It prevents oxidation of foodstuffs, whereas acetic acid is used for preserving or pickling food to prevent bacteria degrading the food. Next thing is acids can be added as a nutrient. Vitamin C can be added to food as a vital nutrient for our lives. And finally, they can be used as a leavening agent, which means rising agents. For example, tartaric acid, along with bicarb sodas in baking powder. You add that to your food. They react together in an acid-carbonate reaction to produce carbon dioxide, which makes bubbles, which causes your bread or cookies to rise. Now, many acids are used for more than one role, e.g. citric acid and acetic acid are both used for flavour as well as other reasons. So that's uses of acids and bases. Move on again, the pH scale. This is the big thing in this course. pH scale is probably the most important part of this focus area. Now, the reason we use the pH scale is the concentration of hydrogen ions or hydronium ions in typical acids and bases ranges from about 1 mole per litre down to 1 times 10 to the minus 14 moles per litre. It's a huge range in concentration. So just to simply simplify that huge range, we use the pH scale. And the pH scale makes the numbers involved much easier to handle. For example, that huge range we talked about up here is simplified to 0 to 14 on the pH scale. So how do we calculate pH? pH is a log scale. pH equals minus a log of the hydrogen ion concentration, or more commonly, as we're going to talk about because we're using Bronsted-Lowry theory, pH is minus a log of the hydronium ion concentration, where those square brackets means the concentration in moles per litre. You can also use that formula to calculate hydronium ion concentration from the pH, and here's the second equation you've got to know. The hydronium ion concentration equals 10 to the power of minus pH. Now, because pH is a log scale, that means every 1 pH change equals a 10 times change in hydronium ion concentration. To prove that, just take a few sample pH numbers, 5, 6, 7, and 8, and using this formula here, you can then calculate their corresponding hydronium ion concentrations. 10 to the minus 8, 10 to the minus 7, 10 to the minus 6, 10 to the minus 5 moles per litre. And it's clear to see that every time you decrease the pH by 1, going from 8 to 7, you're actually increasing the hydrogen ion concentration by 10 times. Every jump down in pH by 1, you're actually timesing by 10 the hydronium ion concentration, or similarly, every time you jump up 1 in the pH scale, you're dividing by 10 the hydrogen ion concentration. So what factors can change pH? Well, anything that changes the hydronium ion concentration is going to change our pH. So if you increase the concentration of your acid, if you increase the strength of your acid, or you've got an acid with polyprotism, they're all going to increase the hydronium ion concentration, and therefore they're going to decrease the pH. Because don't forget, if you increase the hydronium ion concentration, that's the same as decreasing pH. Acids have low pH, bases have high pH. A little bit of extension here. This is sort of hinted at the HSC sometimes, is that water naturally exists in this equilibrium reactions, and we know that most of our acids and bases are aqueous, so every time we add an acid or base to water, we're going to influence this equilibrium, this self-dissociation of water. So no matter how much acid or base we add, adding acid or base is going to add either hydronium ions or hydroxide ions. It's going to shift this equilibrium back this way according to Le Chatelier's principle. But because it's equilibrium, we're always going to have some hydronium and some hydroxide in all acids and bases, no matter how strong they are. And just by an equilibrium constant thing here, this ratio of hydroxide to hydronium ratio, if you times them together, you're always going to get 10 to the minus 14. And this equation here lets you calculate OH from the hydronium ion concentration, or you can calculate hydronium ion concentration if you know the hydroxide ion concentration. Just a little extension, I'm not sure you're going to need it, but just in case, there it is. That also leads to the relationship that pH equals 14 minus pOH. This stuff's here just in case. I don't think we need it in the HSC course though, but who knows. Let's move on. Strong, weak, concentrate and dilute, a very important concept in chemistry, and this has been cut off for some reason, but concentration is the number of moles per litre of acid in solution. Strength is related to the percentage ionization. It's a percentage of acid molecules that have been ionized or donated a proton, if you're talking about the Bronsted-Lowry theory. So if the acid formula is HA, the percent ionization is 100 times that ratio of hydronium to HA concentration. And this little diagram here is perfect. If you're ever asked to explain the difference between strong, weak, concentrate and dilute, this is the diagram to draw. We have concentrated, which means large numbers of moles of acid per litre. So lots and lots of acid molecules in this region here. Dilute, not many acid molecules. But these two are strong because you've got 100% ionization. Each molecule donates a proton. Therefore, you have no intact acid molecules left. They've all been ionized. However, for weak, all these molecules haven't donated a proton. So only some molecules donate a proton. That means they're weak. And you can see the difference here, concentrated up here versus dilute, a lot of acid molecules versus not many acid molecules. We've got strong acids and pH. Now, strong acids we know are completely ionized, or according to Bronsted-Lowry, every molecule donates a proton. An example of a strong acid or a strong monoprotic acid is hydrochloric acid. Now, for strong monoprotic acids, we can say the hydronium ion concentration is equal to the acid concentration. Why? Let's look at an equation. When HCl ionizes or donates a proton to water, you produce hydronium ions and chloride ions. Note the single arrow, which means it goes to completion. It's strong, it's not in equilibrium. But if we look at this equation here, the ratio of HCl to H0 plus is 1 to 1. And that means the hydronium ion concentration will equal the hydrochloric acid concentration. For example, if the acid concentration is 0.0003 moles per liter, you know the hydronium ion concentration is going to be 0.0003 moles per liter, and therefore you can calculate the pH of that hydrochloric acid if you know the concentration of the hydrochloric acid. Now, polyprotic strong acids such as sulfuric acid, the first ionization is strong, but the second ionization is usually not 100%, i.e. not strong. For example, sulfuric acid reacting with water, the first reaction is completion. You've got this arrow here. For every sulfuric acid molecule, you'll produce one hydronium ion and one hydrogen sulfate ion. But hydrogen sulfate is not necessarily a strong acid. It's actually in equilibrium with water to produce hydronium ions and sulfate ions. So the second ionization is equilibrium. It's not 100%, but for very low concentrations, such as less than 1 by 10 to the minus 3 moles per liter, the second ionization is approximately 100%. The reason why that is, we'll look at the next slide. So that means for very low concentrations, you can assume the hydronium ion concentration is twice the sulfuric acid concentration, because for one sulfuric acid molecule, you'll get 1 and then 2 hydronium ions. So if you know the sulfuric acid concentration is 0.0003 moles per liter, that means the hydrogen ion concentration is going to be twice that, 0.0006 moles per liter, and therefore the pH will be 3.2. And you can see that's actually a lower pH than HCl. And that's because both are strong, but sulfuric acid is diprotic, so it's always going to have a slightly higher hydronium ion concentration than hydrochloric acid, and therefore a lower pH than hydrochloric acid if they're at the same concentration. Let's look now at weak acids and pH. This is quite a bit of dense text because a lot of things to think about with weak acids and pH. First of all, weak acids are not completely ionized, and therefore you can always say for weak acids the hydronium ion concentration will always be less than the acid concentration. This means that weak acids will always have a lower hydronium ion concentrations than strong acids at the same concentration. That's because pH is minus log H3O plus. A weak acid will always have a higher pH than a strong acid at the same concentration. And you can actually calculate the percent ionization of a weak acid if you know the pH. So here's an example question to talk about that. The question says, explain why a 0.0003 mole per liter solution of HCl has a pH of 3.5, but a 0.0003 mole per liter solution of acetic acid has a pH of 5.5. Now, both these acids are at the same concentration. They're both monoprotic, so why does one have a different pH to the other? Well, first of all, how you'd answer this question? First of all, you'd say HCl has a pH of 3.5 because, and we've explained that in the previous page. You actually go through and explain why HCl has a pH of 3.5. But for the acetic acid, first of all, you've got to say it's a weak acid, and therefore it's got less than 100% ionization. I would then write the equation down, showing its equilibrium, showing that it is not completion. And you can say, well, if we know the pH is 5.5, you can actually calculate the hydronium ion concentration, knowing that H3O plus equals 10 to the minus pH. And therefore, if this acetic acid has a pH of 5.5, the hydronium ion concentration must be 3.16 by 10 to the minus 6 moles per liter. Therefore, you can calculate the percent ionization, which equals 100 times the hydronium ion concentration divided by the acid concentration, and that tells us the ionization of acetic acid is 1%. Then you can make a conclusion. This is why acetic acid has a lower hydronium ion concentration and a higher pH than HCl at the same concentration. So therefore you've gone through and you've explained why the HCl has its pH, and you've explained why acetic acid has a higher pH. Now, one thing that's come from the HSC a couple of times recently about weak acids is weak acids and diluting. Now, if you look at this weak acid equation here with the 2 stars, you can see it's equilibrium. And as soon as you've got equilibrium, that means Le Chatelier's principle applies. And that means when you're diluting a weak acid, which means adding water, adding water to lower the concentration, by Le Chatelier's principle, if we've raised the water amount, that means the equilibrium is going to shift to the right to counteract that change. If it shifts to the right, that means it's actually going to increase the hydronium ion to acid concentration, and therefore it's actually going to increase the percent ionization or increase the strength. That means the more dilute a weak acid is, the effectively stronger it becomes. And that's why H2SO4 becomes a stronger acid, or almost 200% ionized at low concentrations, because you're adding so much water, it causes that second ionization to go to completion. Now, one last note, for polyprotic weak acids, e.g. citric acid, the second ionization has an even lower percent ionization than the first, and so on and so on. And that means the effect of the second and third ionization in water only has a tiny effect on the hydronium ion concentration, and thus the pH. But when we're adding it to strong acids and strong bases, as opposed to water, it does make a difference. And just for the record, the acids you've got to know, HCl as 100% ionization is strong, acetic acid has about 1% ionization, and citric acid is the third one you've got to know, it's got about 8% ionization. Now that's the official end of this talk, the end of the supposedly 5-minute review, but by request I'm going to go through some particular pH questions from the HSC, so stick around if you wish. The first of these questions is this. Now have a look at this question. It's asking you to calculate pH. It's asking you to compare the pH of sulfuric acid solution to the hydrochloric acid solution, and then compare the hydrochloric acid to the acetic acid solution. So pause the video now if you want to do this, have a go at the question, and then press play if you're stuck or want to check your answer. Pause now. Okay, now let's have a look. If you want to check your answers, if you think you got it, the answer's on page 34 of Success 1. It's actually question 7. If you are stuck though, here's some hints. First of all, to calculate the pH, use the formula. Second hint, if you're not sure how to answer the second question, remember, sulfuric acid is diprotic. So what does that do to the hydronium ion concentration? And according to the pH formula, what will that do to the pH? Third one, explain why acetic acid has a higher pH. First of all, don't forget acetic acid's weak. Because it's weak, what does that mean for the hydronium ion concentration compared to hydrochloric acid? And therefore, what will that do to the pH compared to hydrochloric acid? Let's have a look at the next question. The next question is this. It's a multiple choice question. Pause the video now, have a go. If you get stuck, unpause it and see if you can check your answers. Alright, hopefully you've had a go at this. If you want to check your answers, you can see page 31. It's question 14 is Success 1. If you're stuck though, here's some hints. First of all, don't forget that sulfuric acid is diprotic. What's that going to do to the hydronium ion concentration? And therefore, what's that going to do to the pH? Let's have a look at the next question now. The next question, let's have a quick read of it. What you've got to do is explain the difference in pH between these three different acids. Acetic acid, citric acid, hydrochloric acid. They've all got different pHs. So have a go at this question now. So pause the video. If you get stuck or want to check your answer, press play and we'll try again. Or we'll have a look at the answer on the next page. Alright, let's have a look at the answers. If you want to check your answer, if you think you got it, page 128 of Success 1, it's question 24C. We'll give you some advice. If you're stuck though and want to have some advice before you move on, first of all, don't forget hydrochloric acid strong. So can you calculate the pH of hydrochloric acid, or can you confirm the pH is 2 for that particular acid? For the other acids, they're both weak. So can you explain why that makes the pH higher than the HCl? And lastly, they've got different pHs. They're both higher than HCl, but they've got different pHs. Can you explain that difference between acetic and citric based on their strength and thus their hydronium ion concentrations and thus their pH? Let's look at the next question. This question is, you've actually got a solution of hydrochloric acid and a solution of ethanoic acid. They're at different concentrations, but they've both got the same pH. Have a go at answering this question. If you get stuck, turn to the next page. So pause it now, have a go. You'll get some hints in the answer on the next page. Let's look at the answers. Answers on page 394 of Success 1. It's question 21. If you need some hints though, first of all, they've both got a pH of 3. So can you calculate what the hydronium ion concentration must be for both? Is that consistent with what you know about the strength of hydrochloric acid? And if you've calculated the hydronium ion concentration, what does that mean about the percent ionization of acetic acid? And therefore, can you explain why they've both got a pH of 3 even if they're at different concentrations? Lastly, or not lastly, this is a tricky question. This is a common appearing multiple choice question now. Have a go. You can pause it, have a go. If you get stuck or want to check the answers, press play. Alright, the answers are on page 306. It's question 14 of Success 1. Hints. What's the reaction equation? What's the mole ratio? How many moles of each have you got? You've got a certain concentration of volume, and a concentration of volume is one limiting. How much the other remains? How many moles of hydronium ions remain? What's the final hydronium ion concentration? Remember to use the whole volume for your concentration calculation. And then what's the pH? Alright, next question. You've got equal volumes of 4.1 mole per liter acids that are titrating with sodium hydroxide. Which one requires the greatest volume of base to change? Have a go, press play again when you're ready to check your answers or get some hints. The answers are page 392 of Success 1. It's question 7. Some hints. What is strength? Remember, it's percent ionization in water. But don't forget, sodium hydroxide is not water. We're actually not adding these acids to water, we're adding them to sodium hydroxide. It's a strong base. Therefore, percentage ionization in water is irrelevant because all acids donate all their donatable protons in sodium hydroxide. So write an equation for each. Which one requires the most sodium hydroxide to neutralize? Okay, this question's got 3 solutions. They're the same concentration, 0.1 moles per liter. It's acetic acid, citric acid, and hydrochloric acid, and the pHs have been measured. Which solution's got the highest pH? I'll try and explain this right this time. Pause the video and have a go at the question. When you're ready to check your answer or ready to get some hints, press play. So pause now. Alright, if you want to check your answers, you can go to page 480 of Success 1. It's question 11. But if you're stuck, let's have some hints. Does highest pH mean most or least hydronium ion concentration? Now they all have the same concentration, so the only difference between the 3 acids is going to be their strength. And remember that polyprotic acids and weak acids have only a minor effect on the pH. So based on the strength of those 3 acids, the one with the highest pH will be... Let's see if you can figure that out. Let's go to the next question. This next question, I think, is the last question in our set. It's got a little table here. It says, which of the following changes take place when 50 ml of water is added to 50 ml of 0.1 mole per liter acetic acid? Now, have you got the question and pause the video? If you want to check your answer or you're stuck, you can press play. So pause the video now. Okay, if you want your answers, see page 480, question 18 of Success 1. If you want to get some hints, and I'm not surprised if you do, this is quite a challenging question because the question's got 2 parts. The first part is talking about the pH. Now, if the solution is diluted, will that raise or lower the hydronium ion concentration? And will that raise or lower the pH? But be careful with that, don't get tricked with that. The second part of the question is what's going to happen to the degree of ionization. Now, first of all, acetic acid's weak, so it exists in equilibrium with hydronium ions. And a big hint is write the equilibrium equation, showing it donating a proton to water. Now, based on that equation you just wrote down, and Le Chatelier's principle, what will happen to the position of equilibrium if you add water? Now, once you figure that out, does that make the percent ionization increase or decrease? So have a go at that question and check your answers. And I hope this video has been helpful for you.